Hey, how's everybody doing? Welcome back to the Math for Healthcare video lecture series. We're going to continue with some logarithmic functions. What I have up on the screen here is a little bit of a review of what we did last video, and then we'll see how to use them to solve exponential equations. So first is, remember the definition. This is y equal to a to the x is the exponential form of log base a of y equals x. In other words, what does the log function do? Well, you could think of it as it's the inverse. It undoes the exponential function. But another way to think about it is, what do I raise a to in order to get y? In other words, a to the x equals y. So now in the bottom of my screen, I'm going to make it a little bit bigger here. I have the natural log function graphed, which is in purple, and the exponential function, which is in black there, and then the line y equal to x, because it just gives us an idea of how they're related. Basically, you just switch their x and y values and you'd be on the other one. Okay. But again, as we have natural log of x, what does that mean? That's log base e. Log base e is what I mean by that purple curve. And y equal to e to the x is the inverse of that. And then just reminder is log x, written out log(x), is log base 10. Okay. Now, the example here went over a little bit, and I'm going to put in those two functions basically let's take a look at 2 to the x and log base 2 of x. And since 2 to the third equals 8, log base 2 of let's see, log is f of x, so log base 2 of 8, of course, should be 3, and we see that. Okay, so what is it really doing is, as far as the log function and the log base 2 of x, remember, it's the exponent. We're always dealing with the exponent, right? So, okay. So here, what are we doing? We're going out here, 2 to the 1. Okay, 1, 2 here, right? So what do I raise 2 to get 2? 1. There we go. Log base 2 of 2 is 1. And so on and so forth as we move out our line here. Right, it's growing really slowly because we're only talking about what's this, 50. Okay, 50 is somewhere around what? 2 to the, let me think about this. 6 is 64, so okay, so log base 2 of 50 should be a little bit less. Should be less than 6, probably more than 5, because 2 to the 5th is 32, okay? That's the idea of those graphs. So logs are getting at your exponentials, all right? The exponents, not exponentials, getting at the exponents. So let's see here if we what that means for us. All right, a couple things. The identities here, they help us out. All right, log a raised to log base a of x is x. Okay, why? Because log base a of x is, what do I raise a to get x? Well, I'm going to end up raising a to that. All right, and log base a of a to the x is equal to x. So again, these two tell us logs and exponentials undo each other. All right? And log base a of 1, no matter what the base is always going to be 0 because what do I raise a to? No matter what it is to get 1, it's 0. Now, this one down here is called the change of base formula. And it's not too bad to describe that, right? We want to get it. That's a way to evaluate if you have a log in a different base than your calculator accepts. So for instance, here is, well, let me think. If I'm looking for log base A of B, okay, that's equal to some number, let's say x. We're trying to get at x, right? What's the exponential form here? A raised to the x equals B. Okay, yeah, that's pretty good. And let's see, what if I take the natural log of both sides? Natural log. We get x natural log of A equals the natural log of B, and finally x, which is log base A of B, equals the natural log of B over the natural log of A. If you didn't quite follow that, that's okay. This is really a formula, and you're welcome to write down and use it as part of your notes. But it's just a change of base formula, way to evaluate things before we were able to evaluate other stuff. Okay. So again, why is that change of base formula is really just a way, okay, 2 to the x equals 5 over 5 halves, or log base 2 of 5 halves. Well, that's the log of 5 halves divided by log 2. But notice in the modern era here, in Desmos, I could put in log base 2, and that's totally okay with me. You guys, whichever way you want to do it. But let's see here. We get, looking at f of 5 halves, okay, and that's should be approximately 1.32. Does that make sense? Well, let's see. 2 squared would be 4. What's 5 halves? That's 2.5, right? So, and 2 to the 1 is 2. So it's got to be somewhere between 1 and 2. And another, just so that you see it does work out the same as I could do the natural log of 5 halves if you're working on a calculator. Oops. Got to get out of those parentheses. Divided by the natural log of 2. And there we see the same answer. And that's our formula for our change of base. Now, how are we going to use this for solving exponentials? Well, we need some other properties. One is log base A of x times y equals log base A of x plus log base A of y. Note, log base A of x plus y not equal to log base A of x times log base A of y or whatever. Okay? It's important to... Now, why is it this works? Notice this is kind of similar to what we did for the exponents, right? Two things had like bases, we multiplied them together, and logs, look at, we add their exponents, and that's exactly where this is coming from. Let's think about it as an example. Log base 2 of, let's say, 2 cubed times 2 to the 5th. Well, we could evaluate this. We know this is going to be log base 2 of 2 to the 3rd times 2 to the 5th. We add them, we get 2 to the 8th. And I want you to think about that. Log base 2 of 2 to the 8th is, pause it if you need to, that is 8. On the other hand, our rules tells us this is log base 2 of 2 cubed plus log base 2 of 2 fifths. And there we get 3 plus 5, or 8 as well. And it's that idea. They're talking about the exponents, so that's why that rule works out. When we multiply bases over here, we add the exponents over here. Inside you have everything. Outside of the log, it's the exponents. So that's really where this formula comes from as well. Same thing. And then it's also where this is the most important one on this page. We use this over and over again. This is our power rule. Log base A of b to the k equals k times log base a of b. Why does that make sense? Think about it in repetitive multiplications of things with exponents and similar bases, or it's kind of like raising something with an exponent and then raising that to a power, and we multiplied those things. Okay, similar idea. But anyway, it's a formula we'll use, and really what we use the most is the most used here for that formula is natural log of b to the k equals k times the natural log of b. That's going to be 99% of the time when we're solving exponential equations, we're going to use this rule. So let's see how that comes up. Okay, so for instance here, I have e to the 2x equal to 37, all right? If you recall, this was something we had when we started with logs, was, well, how do we get things out of the exponent? Well, now we know how to do it. Here, this works out evenly. I could say, take the natural log of both sides, natural log of e to the 2x. As long as I do it to one side, I could do it to the other with the natural log. And now, oh yeah, what's the natural log of e to the 2x? Those are the same bases, so that just ends up being 2x, and then equal to the natural log of 37. So that x equals the natural log of 37 divided by 2, which is approximately, I'm going to have to plug that one in my calculator, but you could find the natural log of 37, and let's see here, divide by 2. And that's basically all we need to solve most exponential equations, all right? Let's look at number 2 here. And here, try to estimate what x should be before using algebra and logs, all right? Well, let's see, 2 to the x equal to 15. Well, 2 cubed is 8, 2 to the 4th, 2 cubed equals 8, 2 to the 4th equals 16, so x should be approximately a little less than 16. A little less than 4, right? Because 4 would have gave me 16, so I'd say something like 3.8-ish or something. But let's see exactly. So we go here, notice the base is 2. But I'm not going to use log base 2 here. Every time I'm solving equations, I use the natural log, because it's only recently that we could evaluate things besides the natural log in our calculators. And now we use the power rule that says that this is equal to x times the natural log of 2, and that's still equal to the natural log of 15, and we get x equal to the natural log of 15 divided by the natural log of 2, and we'll check that in our Desmos. 15 divided by ln of 2. Oh, so it's about 3.9. All right. Now, last equation here, we have, let's see, e to the 2x minus 1 equals e to the 2x minus 1 equals e to the 0.2x. How are we going to solve that? All right, well, we got to undo the e, or we got to get it out, so we got to get the variable out of the exponents, so we take the natural log of both sides, and then, all right, they cancel each other out in a sense, so we get 2x minus 1, right? What do I raise e to get 2x minus 1? Well, it's 2x minus 1. Equal to, what do I raise e to get e to the 0.2x? Oh, 0.2x. Okay. And now we do subtract the 0.2x from both sides, add 1 to both sides. We get 1.8x equals 1, and x equals 1 over 1.8. I'll let you find what that number is, but it's, look, it's got to be close to a half, right? It's probably like 0.4 something. All right, so that's basically how to solve exponentials. So in the next video, we'll look at application problems and come back to that compounding interest one where we want to know how long it took us to get to $10,000. But first, just as we also need, well, what about things that are modeled in natural log? Okay, so for instance, natural log of x plus 2 equals 5. What I do is say, if these two are equal, then, and sometimes people just write it like this, then e to the natural log of x plus 2 has to equal e to the 5th, okay? And now, oh yeah, these undo each other. E raised to the natural log of x plus 2 leaves me with x plus 2 equal e to the 5th, and x then equals e to the 5th minus 2. You could plug that in and get a decimal if you want. It's not worth it for us to do it here. We'll do it on the application problems. And now, all right, this one's a little more complicated. Here, what? Oh, we could use our formula. This is equal to the natural log of 5 plus 4x over 3 plus x. And that's still equal to the natural log of 3. We didn't change that, right? Minus, it's like subtract, you know, what is that? It's like when we divide things, things with like bases, we subtract their exponents. All right, now we could take e, we take both sides, raised to the e, or e raised to each side has to be equal, and it undoes our natural log. So then we get 5 plus 4x over 3 plus x equal to 3. Now, how are we going to solve this? We're going to multiply both sides by 3 plus x, so we get 5 plus 4x equals 3 times 3 plus x. All right, and I'd like you to finish that one on your own, solve for x and plug it back in and make sure it works out. But that's basically how we use exponential and logarithmic functions. All right, the next section is going to deal with, this is that banking example, and I'm going to do that in another video tomorrow. But you're more than welcome to try the solving the applied ones, and you know you're not using anything different than the tools that we just learned there. And don't forget to